Right. If you'll all have a seat, we'll get started. Okay, everybody. Welcome to How Things Work, the spring version, Physics 1060. I'm Lou Bloomfield. I've been doing this a long time, but it's sort of one of my missions in life, is trying to teach physics to people who aren't planning on going into physics. So welcome to this course. Some of you I've seen before in 1050, and many of you are new, but anyway, glad to have you. The seating will loosen up, the tightness of the seating will loosen up because you all know that a little bit down the road, not all of you will go to every class and so on. So it's never a problem. Any of you are not yet enrolled, this semester doesn't look like it's going to be a problem. I think everybody's going to, who wants to be in here can be in here. So how things work, I'll start off today talking about the class, and then I'll do the class, at least I'll start. And as you'll see, it's a object by object exploration of the real world, looking at the physics within the object by object. So just to start off, a little bit of introduction. What's physics? It's really the study of the basic physical world. So it's more basic than typically than chemistry or biology. It's down really into the nitty-gritty. It applies to our universe, I suppose, as opposed to mathematics, which applies to any universe. So it's the details of how our universe works. And not only does it explain things about the universe, but it allows us to predict them, even if we haven't seen them in advance. We can anticipate what's going to happen based on previous observations. In fact, I should say that physics is all observation-based, ultimately. There are people who do the physics of other universes that don't exist, but for the most part, what I would consider to be real physics is based on you look and see things, and then you try to explain them, and then you try to predict them. It's related to the real world, and so it's sort of natural to try to look at the real world as the source of material to discuss physics. It addresses how and why questions, and that's where the physics lives. It doesn't live in the what, where, when. I'll get emails from kids in grade school or something like that saying, we have to do a science project, can you tell me who invented this? And that's not science, that's history. So the how and whys typically have a lot of understanding under them. So that's where we'll concentrate. And I figure that understanding something about physics is a key element of science literacy. So I'm not trying to make physicists out of you in the sense that you'll go off and do physics for a living. But the world around you, you live in a world that has rules, not legislated ones. Just like if you do this, this is going to happen. So you might as well understand some of those rules because they'll prevent tragedy. They'll help you in ordinary life. The other thing is that modern life has become very technically oriented, and all the startups are all about gadgets. And understanding how those work is potentially pretty useful. And furthermore, we as humanity has run up against a lot of technological problems that are going to be coming into crunch time during your lifetime. And understanding how things work, finally, will be helpful in dealing with them, whether you deal with them directly, if there's a future president or two in this classroom, great. If not, still, it all matters. So hopefully I'll give you some background for that. Okay, so what's how things work? That was physics. This is how things work. I consider it sort of a backwards course in physics, and I have been doing it for 25, 26 years. The point being to give you something that's useful, not something that physicists want to pound into you, but rather something that you actually will find valuable in your real life. And the classic approach to physics, teaching physics, is to just get right into the formulas and calculations, and eventually, if there's time at the end of the class, or maybe at the end of the semester, or maybe never, to apply it to something real. So I flipped that backwards. And so we're going to look at objects to the extent that I can sort of keep that conceit going. We look at the objects and then find physics within them, and occasionally there'll be formulas that come up in calculations. But by and large, this is not a calculational centric class at all. You don't need a calculator for anything. If there's a numeric answer to a question, it's usually an interesting number, like 0, or your weight, which is an exact quantity and much better than some number of pounds. So you don't need calculators or any. We leave the math behind. That doesn't make it an easy class. It turns out the concepts, understanding what the heck is going on, is harder than calculating with a simple formula. That's just manipulating numbers on a sheet of paper. Thinking is a more challenging job. And so in trying to make a class that's valuable to you guys, there are a bunch of ways of teaching physics to what some physicists would talk about, like the great unwashed, which is really a sad statement to start with. They'll do stuff like they'll either do the what, where, when questions and call it science, which it isn't, or they'll just do the gee whiz stuff. And so this is officially a love tester. And when I heat the bottom, the liquid goes up to the top. And I'm not very hot right now, so it's going up very slowly. No love. Anyway, but they'll go like, oh, look. Oh, this is science. Ooh. You've been to those things, right? And you learn from this that the guy up there is weird, okay? I mean, weird anyway, but that doesn't matter. I can still teach you science even in the context of weirdness. So making gee whiz stuff, I will do some gee whiz stuff, but in general, my goal is to explain everything, give away all the secrets. It's unmagic, I sometimes talk about it. It's the opposite of magic, where a magician tries to confuse you and confound you and show you something you don't understand and be happy with that. My goal is to give away all the secrets. It's the opposite of magic. So if I do a demonstration, and I do lots of demonstrations, and it doesn't make sense, you don't understand why I did it and how it worked, then I failed. So hopefully I won't do those too much. I mean, sometimes the demonstrations fail for good physics reasons, and they just don't work right, but that's a different problem. All right, so this is effectively the case study method to going through physics. So it's a concept that's well established in other disciplines, and I brought it. I wasn't the only person to ever try this, but I'm the one who stuck with it the longest, to bring case study to physics. So we'll do case study physics and answer those how and why questions. And in part, that's because it was how scientists actually discovered physics, and it's what brought me to physics. Most people who end up in physics, at least in my era, just couldn't help but play with stuff as a kid and take everything apart, try to put it back together. I mostly succeeded. There were a few things that didn't ever go back together again, like the wind-up clocks. The springs come out of them and you can never get them back in. There's some special tool that I didn't have as a kid. All right, so some goals and expectations for this class. I would hope that you'll develop understanding and intuition, so that you'll sort of walk down the street and be able to look and see at things and understand why they're happening. One of you walked in here with a skateboard, and this is right, first class, this is how a skateboard works. Not skating, but skateboard. Like next time you go, there it is. The next time that skateboard goes down the road, think about it. We're going to deal with that, okay? Appreciate the role of physics in the world. It's not just an arcane academic subject. It just lives in the academy. You walk out the door, it's gone, right? This is everyone's dream. You go to college, 4 years of intense work. You walk out, you don't know nothing. Mind is erased, and you come out with your degree. Great. No, I hope this sticks. And our universe is predictable to an extent. It's not perfectly predictable, but for interesting reasons. But it has a patterns to it and ways in which we can understand it. And finally, I hope you'll feel that science is fun, or at least interesting and accessible, that it's not something to be afraid of. I mean, it's not easy, and so you can be afraid of things that are hard, but life is full of things that are hard. You deal with them, and hope you will. This class is not much about memorizing. Naming things, I don't care about naming things, rare exception. It's about understanding. So you have to actually understand the concept so you can apply it to something we've never talked about. But it has this common physics conceptual thread going that connects it to, for example, skating. Skating, skateboarding, ooh, they're connected in very useful ways, interesting ways. What else? I assume no prior study of physics. Some of you will feel like you're really behind the 8 ball here because you're coming and you've never taken high school physics. As I think you will discover pretty early on, I certainly see it, and I can point it out to you occasionally, that people who have taken physics before may or may not have brought much with them. And we'll get to that. But so if you have never taken physics, big deal. I assume no knowledge. We start at 0. And those of you who took the other semester, the fall semester, 1050, will have a 2 or maybe a little more than 2 week review. That never hurt anyone. Sorry about that if you get bored, but if you already can anticipate my silly jokes, I'll try to invent some new ones. All right. So I used to use clickers, but for various reasons, I stopped using them. So now I play the voting with your hand game, back to Victorian classroom. So I'll ask questions and have you vote. And, there's no shame in any vote. If the questions are hard, they're hard. You can't tell whether it's B or C. This one's just data collection. So what is your background in physics? This is in part for your own edification. Going from no physics to, okay, I change this every time. This time it's 3 physics-based startups in middle school. I didn't say they were successful, but just you tried them. Okay, so how many of you have taken no physics in the past? So a good fraction. Some, but I've never taken a physics class. Okay, how about I've taken a year of physics? Yeah, this is the majority, and it always is the majority. 2 years of physics. Okay, more than usual, but a fair number. Okay, and E, this is more fun with the clicker because there are a few people who vote for E. There are a few people who vote for E when there are only 4 answers. But E, okay, somebody's got to do it. All right. Second question, also sort of informational, is these are 6 terms. Physics, they're quantities of physics, physical quantities. And can you distinguish between these pairs? So can you distinguish between the pair? I'm not asking the question yet. Velocity versus acceleration, and mass versus weight, and force versus momentum. You got the pairs? How many think that makes no sense to them at all? Nothing. 0. How about I have a faint sense for the difference between them? Okay. How about I may be able to distinguish? I might be able to do it. Okay. How about I probably can distinguish them? Okay. We're about even between C and D, and how about E can definitely distinguish them? Smaller fraction. So it's peaking between C and D. Of being able to distinguish them. And so we'll go through those. So whether you've got them under control or not, I think it's not going to be a waste for the vast majority of you to revisit them carefully. So some things to do. In general, please look at the syllabus. You're responsible for the syllabus. It's online. I try not to use UVA Colab. I try to use my own website. That's the link to it. It's on this. If you haven't picked one up, pick up. It looks a lot like this. The syllabus is this is a printed version of what's on the website. The fact that it's on the website, it evolves because if I don't keep up with my schedule or get ahead or behind, I will change the schedule to reflect that. What else? Read the ebook. Okay, I wrote the book, and so you'll hear my own voice more or less directly there in the book. But the written versus the spoken there's value in seeing things multiple times. Learning physics concepts is difficult, even for physicists. We have to revisit them. Everybody's got to revisit them. So seeing them multiple times, read the book, hear me say it, talk with your friends, do the problems. All these trips through the same concept will gradually clarify it and settle it in your mind. The book over the years has evolved from a print book to a more, it's now primarily, in my mind, an electronic book, in part because I can make the figures, which used to be static images on a sheet of paper. I can make them move. I can have things happen. And physics time matters in physics. Things happening is a big deal in physics. And so the fact that I could animate some of the behaviors of things like a transformer. You'll see it a month plus from now. We'll come up, deal with the transformer, and you've seen transformers sitting on telephone poles, those big canisters sitting at the top of a utility pole, I guess they would probably go, or the green boxes out in your front lawn. Those are transformers, and how they work is kind of neat and complicated, and it's hard to wave my hands and explain them. So I put this big animated figure. You can see how they work in considerable detail. You can see things you can't see. You can't see an electric charge. There's an electric charge right there, right? Yeah. So I can animate stuff, and I had fun doing that, as you might suspect. Okay, so play around with the online book. It's the only thing you need to get. The print book you can get if you want, but the online book you have to get because that's where the homework lives too, is in this online world. Keep track of the problem sets in the exams. What I expect you to do, 10 problem sets. If you just listen to me say stuff and go and you don't do it yourself, as in do the problem set, it's really hard to learn the stuff that way. You have to suffer over the questions. So the problem sets are required, they're graded, all that. You'll learn, that's where you'll learn a fair fraction of what you're going to learn. The exams, 2 midterm exams, 1 test. You can anticipate what these look like because I post all the old exams. You can find all the exams going back probably till 1995, I think, online on the website for this class and linked to past websites for this class. So you can look at the old questions. There are lots of multiple choice questions, and they're all thinking questions. Very few calculations. Again, calculation has a number. If it's got a numerical answer, it's a pretty simple one. And what else? Oh, there's an online, doing things on the online book will count 10% of the semester grade too. I'm still working. People who were in the class last semester know that this was a complication. And I'm working with them. We're almost there. So being involved in the online world, the chit-chat, there's a bulletin board, a discussion board. Get involved in that. I will try to interact with you all there too. You can answer your own questions, one person to the next. I can answer them, like whatever. I can ask them. All right, my final thoughts. Oh, and before I go too far here, ask me questions in class. If all I'm doing is talking out there, I can play last year's class back. It's on video. You can go watch last year's class. I can play it back. I could go take vacation. So if we don't interact in class, I mean, apart from me being up here and actually doing my antics live and in person, we're missing something. So if I say things that are unclear, or you got questions, or you got insights that I haven't thought of, that I haven't said anything about, ask me or say them. Give us your own take. Some of these objects you have more familiarity with than I do. I know them in principle, but I may never have done them. So ask questions, volunteer in class. Hey, I anticipated my own first line there. Do the demonstrations yourself after class. I have watched over the years people get more and more driven by the fear of missing out, needing to get back to the online world within 7 seconds of the end of class. Okay, if you can resist that temptation, come and play with the toys, please do. That's why I've got them up here. You can see this tablecloth up here waiting to be pulled out from underneath the dishes. Yeah. You're welcome to try this. It is not that hard. Okay, you can do it with or without the wine glass. We'll talk about that in a minute, but it works for good physics reasons. Okay, do the demonstrations. Talk to me before or after class, or come to my office hours. I'm happy to talk about anything in office hours, including the problem sets. So if you get stuck on the problem sets, or otherwise, come, bring your friends. That's what I'm there for. This room is open before and after, the whole hour before and the whole hour after this class. So you can come in early, talk with me, talk with one another. Afterwards, you can probably a better time to do the demonstrations. So during class, probably, if you can, come in and out the back the back doors which go into the third floor rather than the second floor. But I barely notice if someone comes in and out of the first floor. This is the second floor, but it doesn't matter. What else? Last thing, electronic devices. It's hard for me to enforce it. My preference would be 0 electronic devices in this room. Why? Because I can't compete with the online entertainment systems that you all have. And a couple of years ago, I put a GoPro camera in the back, filming forward to see what was on all the screens, and it was a bloodbath. And one of the guys back there, not only was he not watching me, but the movie that was playing on his laptop, he wasn't watching that because he was on his cell phone. So he's like, he's a couple levels deep. It's like the Inception, what was the movie where they're a couple levels deep and sleep? Anyway, no science in that. All right, so please try not to use your gadgets. In part, it's not just you who are checked out into zombie land, but there's this wedge of death behind you, of the people who are watching to see, she's buying that? You know, all that stuff. So, okay. Any questions at this point? I intimidated you all. Oh, one other thing is it's my compulsion or passion, I don't know. I will actually try to get to know you, at least by many of you by name. I work hard on it. I have my pictures up here, and I'll work my way. I have to be like in the right mindset to start asking people's names. I'll get some of them. Some of them will just go right through, out, go out, and I'll have to ask you again, or I'll call you by the wrong name. But anyway, I work at this, and only the point is that this should be, okay, it's not a small university, it's not a small class, but my feeling is that it should involve personal interaction. So come and talk to me. I don't bite much, and anyway, I'll stop at that. I want you all to find this a useful experience in every possible way. All right? Okay, so that's my introduction. And so on to the first topic. And so what we'll do is we'll go topic by topic through the world. This semester focuses more on things, as you'll see, that are a little more abstract than the other semester, or not as abstract, but harder to see, because we'll do things with electricity and magnetism and nuclear physics and stuff that's light you can see, of course, but some of the topics are ones that are a little tougher for me to demonstrate and tougher for us to see. But we'll start out the same way I always start out, which is with a few topics that really carry us through the laws of motion and give us, in part, a vocabulary with which to describe things in our world. And, okay, so here we go. So skating. First topic is skating. It's not really an object. It's an activity. And within skating, you can have roller skating, ice skating, skateboarding. There are a lot of things that have the same theme in them. So one thing I tend to do with each new topic is to ask you a question, which, if ideally designed, and some of them are, some aren't, is puzzling at first, and then becomes clear. So here's the first question. The first question is this: is rotary lawnmowers, which are by far the dominant type of lawnmower these days, have there's a metal cage around a spinning blade. The blade is going like crazy. Around in a circle, it's rotating, and it cuts the grass. And the question is, suppose that the grass, the blades of grass that are sticking up are coming from plants that are not rooted in the ground. Real grass has roots, right? Suppose there were no roots. The blades of grass were just standing up somehow on flat ground and not attached to the ground. Could the spinning blade, still cut them? You okay with the question? Any questions about the question? So just get rid of the roots. Just let the grass just sit there minding its own business, and the blade still cut them. How many think yes? How many think no? Okay, so the vast majority are going for no. So we'll come, as I said, we'll ask this one twice. I ask it first. We'll perk along for a while, and then we'll come back to it. All right. So some observations about skating, and rather than putting skates on, which will probably cause me to end up across in the emergency room eventually, I'll use a razor scooter, which is yet another example of sort of the same physical issues. The observations are these, that when you are at rest on a level surface, on skates or on a skateboard, which I have skateboards downstairs and they're death for me. I cannot stand on them for more than a very short period of time without trouble. Anyway, so if I'm on a razor scooter here and nothing's pushing on me and I'm level ground and I'm at rest, I tend to stay at rest. You have never seen somebody just standing there on a razor scooter suddenly head off to the right at 12 miles an hour. This doesn't happen. So things at rest tend to stay that way. On the other hand, if you are moving, you tend to keep moving. It's imperfect, but you tend to keep going. You don't just abruptly stop for no reason. To make the changes, to go from being at rest to moving, you need to get pushed by something. And in this case, the push is actually coming from the ground. It's my other foot. My other foot and the ground are pushing on each other. And that changed me from being at rest to moving. And similarly, to go from moving to at rest involves some pushing as well. So at this point, the takeaway messages are things that are left to themselves. If they're at rest, they tend to stay that way. And if they're moving, they tend to stay that way. Just observations about the real world. It was more complicated, finally it's more complicated because there are things around that are nuisances like friction, which I'm going to try to sweep under the rug for a while. There not being a rug here, it's hard. Okay, so also in dealing with objects, my tendency, my pattern completely, is to ask a series of how and why questions. You notice all these questions start with how or why. And so like, why do you remain motionless? Why do you keep moving? How do you describe motion and stuff? And so I'm going to work through these questions approximately. And as we do this, we'll flesh out some of the physics that shows up. All right. So the first question. The first one is just, why does a motionless skater tend to remain motionless? So the skater just pick some little kid who's able to stand upright successfully on the skates and just sitting there sort of waiting for something to happen. They're not going to start moving by themselves. At rest, they tend to remain at rest. And that is an observed behavior in our universe, that things left to themselves at rest stay at rest. It's given a name. It's called inertia. And you've heard the term inertia many places, often not so much physics context as in carried over into real ordinary life, like you're failing to send in your tuition check because of inertia and subsequently having all your courses canceled. So objects at rest tend to remain at rest. And I can show you this in action. So the traditional first demonstration in this class is the demonstration of inertia. And we'll go up for full degree of difficulty here. It's disappearing ink because of previous disasters. Doesn't always work. So these are objects at rest, and it is their nature, like everything else, when left alone, to stay at rest. This plate will not just abruptly head off that way. It's at rest, it's going to tend to stay that way. I'm going to pull a tablecloth out from under it, and as I do that, I will bother the plates and silverware and wine glass a little bit by way of friction, which is something that's in our future. So friction is a nuisance for today. And in order to minimize the effect of friction, I can't get rid of it. I can minimize its influence by going quickly so that it has very little time to cause trouble. So I'm going to go fast. I'm also using a slick tablecloth. It's silk. It's the ugliest silk tablecloth. And why did they ever make this? I don't know, but we've had it forever. It's gone in a lot of places. So I'll go quickly, and the result is that these objects will do their best to show you their own inertia, their tendency to remain at rest, having started that way. And for those of you who want to come up afterwards and try it, probably without the glass. This is in principle unbreakable, right? Concussion! Oh, yeah, without the anyway, you're welcome to try it. Please do. And so to do it right, just to give you a little heads up on this, go far from the table, move in like this, so you can get your hands moving before you pull taut and the tablecloth begins to move, and pull a little down, not up, a little down, and that will make sure that the tablecloth slides. Ready? Get set. I was noticing the last minute, there's a little rock here. And I was deciding whether I wanted to stop and fix it, but I didn't. Okay. So, why did those things stay there? Because of inertia, right? So it's their nature to do this. There's no magic. It's completely non-magic. It's not a trick at all. Alas, there are videos online that are phony that do this. There's one video of somebody on a motorcycle pulling the tablecloth out from underneath an entire banquet table of stuff. That's phony. The physics is all wrong. It's a steady, it's never going to happen. So alas, you live in a world where they can fake you out into stuff that's not physics. This is one case where seeing it live makes a difference, because I'm not actually a hologram up here being phonied up. It's real. All right, another version of that same demonstration is this. If I put a apple there, minding its own business, it's just sitting there, and I come up and I go through it very quickly with a knife, I can cut it without holding it in place. Rather than do that, and I used to do it like this. Right. Some time ago, a couple years ago, I made this. So I've got a spring-loaded knife. Ha ha ha. All right. I should, I should make an egg slicer like this. Wouldn't you like to have this around your house? Whew. Where'd your fingers go? Okay, so again, what held the apple in place while the knife snuck through it was inertia. The knife exerts a small force on it, which is why it didn't actually completely stay in place, but that was inertia going. Just before I finish with inertia, there's a second half to it. The second half to inertia is that an object, a skater, that's moving tends to continue moving. And this is a familiar thing you've observed. And it's also considered to be part of inertia. So an object at rest remains at rest, or tends to remain at rest. An object in motion tends to remain in motion. So that's the second half of inertia. And to demonstrate this, first off, a banana at rest tends to remain at rest. There's another nuisance around other than friction, and that is gravity. So if I let go of this banana here at the surface of the earth, near the surface of the earth, if I let go of the banana, it doesn't remain at rest. Well, that's because gravity pulls down on things. And that's unavoidable. I cannot turn that off any more than I can truly get rid of friction. I minimized friction up there with a slick tablecloth. I minimized it here with a very fast knife. I'm going to minimize the influence of gravity, again, which I can't get rid of. By doing everything so quickly, gravity doesn't have time to cause much trouble. So if we say that object at rest remains at rest, if I only worry about it for a small fraction of a second, it pretty much stayed at rest. Okay? And an object in motion is going to pretty much stay in motion, actually in a straight line at a steady pace. Now, if I go slowly, it doesn't actually go in a straight line at a steady pace. It falls, and that's a topic for the future, near future. To minimize the effects of gravity, again, I'm going to go fast. And so if I go fast enough, an object in motion tends to remain in motion in a straight line at a steady pace. The story starts after it leaves my hand. I'm going to get it going. Okay? It went pretty much in a straight line at a steady pace. You okay with that? And just to conserve bananas, I'll make my class green. Well, green and yellow. I'm going to let it encounter the blade. Okay? I'm not going to be pushing it when it gets there. I'm going to so the story doesn't start until it leaves my hand. My hand is not going to be here. I can guarantee that, man. All right. Okay. So, who killed the banana? It wasn't me. The banana did it itself. Inertia, right? It was moving to the right at a steady pace, straight line, and the knife just got in his way. I had no role. I'll clean this up so we don't do one of those banana peel troubles. Okay, so at this point, I've illustrated most of inertia. Things that are at rest tend to remain that way. Things that are moving tend to continue moving, turns out in a straight line at a steady pace. We'll do that more carefully shortly. But any questions at this point? I guess sort of the basic idea. And that brings us to, anticipate where I'm going to end up here. Yeah, it gives us a law that has become known as Newton's first law. This is a very primitive version of it, version 1. And so a primitive version of Newton's law, based entirely on observation of the real world, is the following. It's that an object that's free of external influences, you leave it alone, it moves in a straight line, and it covers equal distances in equal times. So it's got a steady character to its movement. That suggests that things always move, and this is where a physicist's sensibilities come in play. That moving in a straight line, covering equal distances in equal times, there's a special case in which the distance traveled in equal times is 0. You're not going anywhere. That's the at rest part. So an object that is at rest and stays at rest is a special case of this, and it's included in this statement. So that's the little yellow note at the bottom. 0 movement. Physicists do this all the time where they talk about an object's moving at 0 speed. And you go, well, it's not moving at all. And physicists will say, well, yeah, well, it's moving at 0. 0 is special, it's good. You're not moving. Okay, so you got to live with it. It's just the way it is. So an object that is left alone, no external influences, it moves in a straight line covering equal distances in equal times. Okay? It's observed in our universe. This was not a trivial observation. It may now, in retrospect, seem like obvious and simple, and who cares? It actually took thousands of years for people to really get this one right. It's Galileo and Newton and people in that era who managed to finally figure this one out. Friction and gravity, I think, really made this one not so obvious. It didn't occur to them to throw the banana fast. Well, maybe it did, but maybe they didn't have bananas. It was hard to buy them. The grocery stores weren't open. All right. Back to this question. Remember this question? Rotary lawnmowers, cutting grass. So a rotary lawnmower spins its blade rapidly over the grass and cuts the top off the grasses. Would the blade still cut the grasses if they were not attached to the ground, but just standing there upright? You okay with the question now? How many think, yes, it could still cut the grasses? How many think, no, it couldn't cut the grasses? Oh, you got it. Oh, and there are a couple of holdouts, but okay. What would keep the grasses in place for the blade to cut them? Inertia. Yeah, glue. Grasses. Spaghetti fettuccine. Ready? Ah, they're all shattered. I cut the grass. I'll send you the bill tomorrow. Yeah, there's no problem cutting grass. It's just sitting there. unattached. The fact that the grasses are attached by way of roots to the ground is almost irrelevant. The blade spins so fast, and there's actually target speed is about 200 miles an hour, the cutting blade, and it should be sharp. Why do you sharpen the blade of a rotary lawnmower? What's involved? It's actually cutting the grasses, and they are remaining in place because of inertia, and the blade just sneaks through them, just like the apple. And if you let the blade get dull because you've driven through somebody's rock garden, it happens all the time. It will not cut the grass very well. It smooshes them. It's like hitting it's the difference between cutting the apple this way and cutting it this way, right? Okay, you get made up applesauce. I have fun. I hope you do. Okay, so furthermore, there are things known as mulching lawnmowers that deliberately cut the grass once, try to lift the grass up by way of airflow, and cut it again, and cut it again, and cut it again. They try to dice. They're basically a food processor. They try to dice the grass into such little pieces that the grass then settles into down to the dirt level and becomes part of the dirt pretty soon. So this effect, I should say, not only does it apply to lawnmowers, it applies to food processors, blenders. You're making your favorite beverage. You put the ice in, you put the other things in that you're supposed to have or not supposed to have, and you hit the power switch, and it's all just diced into little, it's a smoothie or whatever. What held the ice cubes? Inertia. So I would say Friday night, but it's actually Thursday night. Thursday night, when you're doing this, think of physics. Okay. So how do we describe the motion of a coasting skater? And the word coasting is sort of loaded because that by itself is an interesting notion. Skaters spend a lot of their time moving steadily, straight line at a steady, covering equal distances in equal times. That movement, inertial movement, the movement that inertia has in mind, is a concept that familiar as coasting. That's what it means to coast. A roller coaster. What's the coasting thing? It's moving as inertia had in mind. So, skaters tend to move, if they're left to themselves and not being pushed on, they tend to move at a constant speed in a constant direction. That's coasting. And this then prompts us to start developing some words, some language, physical quantities in particular, with which to describe this kind of motion. And I need to work, I'm heading towards velocity, but I can get there in 2 steps. First, physical quantity to talk about. So this is by physical quantity, I mean it's a quantity, something you can measure, a specific amount, and it's physical because we're not talking about dollars or number of sheep. We're talking about something that's associated with the physical universe. So the first physical quantity is position, and position describes where an object is. And it turns out to describe where an object is, you need there are a couple of pieces you need to assemble. First off, you need to define what's position 0. You need a reference. You need everyone's got to agree. If you're going to try to call somebody up on a telephone and tell them where Bloomfield is located, you have to have a reference. Everybody's got to agree on it. And the reference, my classic reference point is the top of these 2 monitors where they meet, right there. That's position 0. And so, hey, position 0 between the 2 monitors. Got it? Yeah, I got it. Okay, so that's position 0. And starting from that reference, you can locate where anything is. And in case where the issue is where am I located, you could say 6 feet. I'm actually about 6 feet from position 0. So you call up your friend up and say, his position is 6 feet from the reference. And the person on the other end goes, okay, that's pretty good. I know about where you're located. But this is 6 feet, and so's this. And so's this. And if I could float, so's this, okay? They're all about 6 feet from the reference position. So there's a second part that's necessary, and that is the direction from the reference to where I'm located. So if you want to fully describe where I am located, my position is 6 feet from the reference in the direction directly toward the front of the room, horizontal direction directly in front of the room. So it's got 3 parts to it. It's got the reference, what's position 0, and the distance and direction that you go from the reference. Those 2 pieces, distance and direction, that lump of information is known as a vector. These are vector quantities, and vector you probably encountered before somewhere, maybe mostly in mathematics. A vector quantity is one that has not only an amount, like 3 cups of water or 5 sheep, it's also got a direction to it, and that's irrelevant to water or sheep, but it's important for position. Direction being which way the quantity extends. So my full position in this case consists of a distance and direction from the reference position. Is that okay? And how you measure the distance, you will typically use standard units. Units is a story that we can get lost in the story of units, but units are conventions where we all agree on this is 1 foot of distance. This is 1 meter of distance in the metric system. The transition from the old English units, or whatever they're called, to the metric or standard system international, SI system. That transition has been going on my whole lifetime. It's going to go on through your lifetime. It's probably never going to fully happen in the U.S. So this is the standard distance, short distance measure in our local units, 1 foot, right? You all know that one. This is the shorter measure, 1 inch. This is the standard. Internationally, this is the real standard of distance, 1 meter. It's about like that. Anyhow, to measure distance, you can't just say 6. 6 what's? 6 millimeters? That's only this big. You need to associate the unit, the conventional unit, in your distance so that people really know what you're talking about. 6 feet, good. 2 meters, also good. And the direction. So that's position. Any questions about position? That leads us then to the quantity I'm more interested in, which is velocity. Velocity is the rate at which position is changing with time. So right now my velocity is 0, because my position's 6 feet toward the board from the reference. 6 feet, it's still 6 feet, still 6 feet, nothing's happening, boring, velocity 0. But if I begin to move, and I'll go 1 meter per second. I'm moving 1 meter per second, and it's not just, I'll go slower, it's too fast, I run out of room. I'll go 1 foot per second. So I fall over while I'm walking. It's because I'm talking. I can only do one thing at a time. So I'm moving at 1 foot per second, end of story. And that's part of my velocity. Clearly my position is it's got one value now, it's got a different value, a different value, a different. So clearly my position is changing with time. How much is it changing? It's changing by 1 foot per second. But I need a direction to that too. Because this is 1 foot per second. But so is this. This is dangerous. Who spilled all the grass on the floor? So those are both 1 foot per second. The difference, of course, is that their directions are different. So velocity is another vector quantity. It has an amount, that being how fast you're traveling, in other words, speed, and it's got direction, which way you're going, which way your position is changing. So this is a velocity of 1 foot per second to your right, and this is 1 foot per second to your left, and this is 1 foot per second down, and so on. All right? So where we're going to go with Newton's first law, second version where I'm going to finish, is we now can change the wording at the end where it said an object that's left to itself, no external influences, moves in a straight line at a steady pace, covering equal distances in equal times. We can reword that last part as it moves at constant velocity its direction of travel, and its speed, how fast it's covering the distance. Those are constant. It coasts. All right? So with that, then, I'll stop for the day, and we'll continue on Friday.